Alright, hey, I'm going to talk about something I don't normally talk about, which is op amps. Op amps are magical. They do these crazy things, and they're one of the simplest things in the world to analyze as far as electronic circuits. They have a really simple behavior, but from this simple behavior, we get all these complex functions. So I'm playing around with audio input to the Songline processor, and audio input is an alternating signal, right? And it's usually centered around zero, so it goes positive and negative, and it's also very small. And the Songline processor expects analog inputs that range between 0 volts and 1 volts. So what I need to do is take an audio signal that's wiggling up and down around 0, and I need to shift it up so that it wiggles between say 0 and some positive voltage, and then I need to amplify it because right now it's going from 0 to about 0.1 volts, and I'd like to have it go from 0 to 1 volts. So my goal is to take an incoming waveform, shift it up by adding a bias, and then amplify it to make it larger. And so one op amp will do that. So this is an op amp adder circuit. It takes two inputs, adds the voltages together, and then amplifies it. And so I have a variable resistor here feeding negative 3.3 volts to 0, so I can get any negative voltage that I want here, which I'm going to add to my incoming audio signal to shift it down to make it strictly below the x-axis, so it'll go from 0 to some negative voltage, and then I'll amplify it by controlling this variable resistor. And this is actually an inverting amplifier circuit, so if I amplify it by 5x, it will not only make it bigger, but it'll flip it, and it'll become positive. And so this is pretty simple to hook up. I have a an old, a nice new PC power supply. And this is mainly giving me negative 12 volts over here, positive 12 volts on my rails, and then ground coming in here to my ground rails. And this is an op amp. This is an LM324. And then these are two variable potentiometers, and it's just the circuit that's presented on paper. So if we go ahead and turn on an oscilloscope, so let me put this on over here. Alright, so there's an oscilloscope, and my signal source is a small metronome, which also has a calibration option, so it'll generate an A440. Alright, so let's go ahead and take some readings here. So I have a metronome with a calibration option, so it will generate an A440. So let me take my scope probe, hook this end up to ground, and I can take a reading on, let's just take it on the output of our calibrator. And so you can see this is generating a 440 hertz tone. It says 440, you can't see that. But this line right here is 0, and so it's going from 0 volts positive. And this is 1 volt per division, so it's going up just about 1 volt. And I can change the amplitude of that by using the volume knob. But 1 volt. So this is just a pure test input signal. So let me go ahead and connect that tone generator to the input of my circuit, and let me hook up my scope probe on the output of the circuit coming from pin 1. And what you see is the same 440 hertz signal, but I can modulate the behavior of this, the shape of this waveform, by using these variable resistors. So this first potentiometer should change the bias, and so by turning this, I can move the waveform up, I can move it down, and normally our waveform is going to be centered around 0, and I'm going to want to bring it to be positive, but whatever the waveform looks like, I can modulate it up or down. So I can add a more or less arbitrary bias to this signal. And then the second potentiometer lets me scale it. So I can make the scale smaller, or I can crank up the amplification and make it larger. So a really simple circuit, right? It's one op amp, it's a handful of resistors, and that's it. But it lets me do this preconditioning that I want on the signal, whereby I can change the center point of the waveform, and I can also amplify it and make it larger or smaller than the original. So so that's just an example op amp circuit, and the analysis of this circuit is actually really simple. Alright, so let's talk about analyzing op amp circuits, just because this is really fun. This was one of the things in studying electrical engineering that really kind of clicked with me, because it's in some ways so straightforward to do these analyses. So let's look at a typical op amp. And an op amp has basically three terminals, two inputs, which we call the inverting and non-inverting inputs, and an output. And you only got to remember two rules for analyzing op amps. One, there's no current flow in or out of these inputs. And two, there's no voltage difference between these two inputs. And those are kind of weird, right? How can there be no voltage difference if there's no current flowing? Because we usually configure these circuits with feedback. So we run a connection between the output and the inverting input, and it goes through some resistor. We'll just call that R1. And so a basic amplification circuit would be something like this. We have an input voltage. We run this through a resistor R2. We take the inverting input, we connect it to ground, and we take the output and we call that V out. Alright, how does V out relate to V in? It takes no more than Ohm's law, and remembering those two facts about an op amp, right? No current flow in or out and no voltage difference. The way this actually works is that, the output will change in such a way that the voltage here is the same as the voltage here. In this case, it's ground, so the analysis gets even easier. So what is Ohm's law, right? You have a resistor, and we have a voltage in response to a current flow. If the current is flowing in this direction and we write the voltage with the positive side on the side that the current is flowing into, then Ohm's law applies, and V is equal to I times R. Volts, amps, ohms. Alright, so what does this tell us about this circuit? Well, we know that there's going to be some current flowing along here. We can draw it like this, I. And so if we label this plus and minus, we can say voltage 2 is equal to R2 times I. And since there's no current flowing in or out of this terminal, all the current that's flowing along here, I, will make the corner come up here and flow across this resistor. So this will also be the same current I. And if we label this plus minus, then the voltage 1 here will be equal to R1 times I. Alright, so we have a voltage here, we have a voltage here, we have a voltage out, we have a voltage in. We want to find V out. How do we do that? Well, we're going to need to know what the current is. Well, that's easy to do, because guess what? We know what the voltage at this point is. It's going to be 0. Why? Because the voltage at the non-inverting input is 0. So this is 0 volts, this is 0 volts. So we can actually solve for I. Since we know the voltage across here is R2 times I, but that's also V in, we know V in is equal to R2 times I, so I is equal to V in divided by R2. And so if we take that current and we multiply by R1, we'll find that this voltage, V1, is equal to R1 times V in divided by R2. So it's just a multiplication of our input voltage by a constant, the ratio of the resistances. Now, be careful with the sign, right? We know that this point is at 0 volts, and we know this voltage V1, we wrote it with the positive side over here, so the output voltage is actually going to be negative. And so V out is the negative value of V1, which is negative R1 over R2 times V in. And that's a basic inverting amplifier circuit. Now, if we make R1 and R2 exactly the same resistance, our output is just the inverse of the input. It's a simple inverter with no amplification or attenuation. But if we make R1 bigger than R2, we start to get amplification and inversion. All right, so that's one piece of our circuit, right? This circuit we were using to add a bias and scale. So that's the scaling part, right? A resistor going back to the inverting input. Let's take a look at what this piece of the circuit does over here. If you have two inputs, so let's say we have our op amp, and this comes down to ground. And I'll just draw this with some resistance R. I'm not going to worry about the amplification for now. So suppose we have V1, which goes through a resistor, and V2, which goes through a resistor. Just like this. We just connect the other ends of those two resistors together, feed them into the negative input, take the output, run it through a resistor, feed that back in also. So we have a big junction here. What do we get when we analyze this circuit? So here's our output over here. Well, again, Ohm's law, V equals IR. So let's imagine we have a current flowing down here and another current I2. Since this is 0 volts, this is also 0 volts, we can solve for I1 and I2. So V1 equals R times I1, which means I1 equals V1 over R. And similarly, V2 equals R times I2. So I2 is V2 over R. And now we have to sum currents. We have a current I1 going into here, I2 going into here. No current flows down this branch. So these currents add together, and what we have coming out here is I1 plus I2. And so here's a voltage at this point. I'll just call this V. And again, Ohm's law says V equals the current, I1 plus I2, times the resistance R. And then V out is just going to be the inverse of V, because again, this is 0 volts, there's the positive side, so this is going to be 0 minus V. So V out will be minus I1 plus I2 times R. Well, I1 and I2, we can write those in terms of V1, V2, and R. So this is minus V1 over R plus V2 over R times R, which is minus V1 plus V2 over R times R, which is just minus V1 plus V2. So there's the analysis of this op amp, and this is a summing circuit. You put two voltages in, and your output is the inverse of the sum of those voltages. Right? 2 volts, 3 volts, we'll get an output of 5 volts, but it'd be negative 5 volts because it inverts. So that's the other part of this, right? This is how I can take in a fixed bias voltage and a voltage coming in from a source. We'll add those together, and then we'll amplify it by whatever amount we tune this potentiometer to, and that gives us our output. So really, really simple and actually really, really fun analysis of op-amp circuits. And again, it's just 2 rules. No current flowing in or out of either terminal, and no voltage difference between the 2 terminals. And any op-amp circuit that you set up, if it's an integrator, differentiator, summing, differencing, etc., same behavior. So, and they're pretty painless to work with on a proto board. If you actually connect this, there's a positive and negative voltage input. Some op-amps like a 741, you cannot get too close to these rail voltages. So if you wanted a signal that could come all the way down to 0 volts on the output, you'd need a negative voltage going into V minus. Some other op-amps like a 324 let you get very close to that negative rail without too much difficulty. But typically, you know, we power these with something positive and negative, plus and minus 3.3, 12, whatever. And then you can work within, you know, that range of voltages as long as you don't get too close to the high or low supply voltage. So anyway, that's just a little bit of op amp analysis. All right, thanks. Bye.